This is actually a story of the Institute, and it starts in about 2008. There were some suggestions that the Institute should be doing something about geothermal, and we thought that was a good idea. So with the help of the Student Sustainability Committee, we conducted a feasibility study of actually implementing a groundwater source geothermal system at Istc. And while it turned out that that wasn't feasible, we actually got together a really great team that was ready to do some work together. And so we reconvened to work on a proposal for some Istc research funding using these types of systems. So initially, we are looking at mapping in Mason County in the Metro East area. And we chose those areas because we already have some data in those areas. We expect to find some resource potential, and we like the urban and rural mix. So these are highly energy efficient systems for heating and air conditioning, refrigeration, and moderately heated processes like grain drying. And there's up to 50% energy savings possible. An advantage over systems that have extensive ground loop heat exchangers is lower installation costs and even better efficiency. So we know that there's lots of resource potential in Illinois and in the U.S. One of the challenges is that successful application requires some site-specific conditions. And so to make this information widely available, we need to do some new synthesis of existing data. And so we think that mapping will help municipalities, government agencies, developers, and businesses be able to identify where there's some opportunities to put these type of systems, and also what is the thermal energy potential at given locations. So a groundwater source heat pump provides heating and cooling by using mechanical power to extract heat from or reject heat to groundwater. And it's an efficient system because water is a good heat exchange medium, and also because of the relatively constant temperature of groundwater. So with all the conditions, what does an appropriate site look like? Well, here's one local example, and they use it for space heating, air conditioning, and refrigeration. They use groundwater and discharge to a local pond that we think is probably connected with the source that they draw the water from. So one challenge is that we need to withdraw and discharge groundwater to a surface. And we don't want to contribute to resource depletion. We don't want to compete with existing uses. So clearly we need to consider some other factors. So what kind of flow rates can be sustained indefinitely? What are the consequences of additional pumping? Can we piggyback off of some existing pumpage? Another important factor is the temperature of the groundwater. That kind of defines the capacity and the efficiency of installed systems. Another important factor is groundwater chemistry and water quality. These factors affect system reliability and maintainability. And they also have implications, really important implications for system design. So we need to consider environmental impacts. We're talking about withdrawing and discharging groundwater, changing the temperature of that, affecting the chemistry, and putting it into a receiving body. So what are the impacts of doing that? Can we spread groundwater contaminants or thermal pollution? And there's also regulatory stakeholders. So we need to find out what does that situation look like when we consider the regulators. And so what we're talking about doing is bringing together all of these factors: availability, groundwater temperature and quality, environmental impacts, and regulatory aspects to define the thermal energy potential at a given location. And so for most people, energy numbers are not that useful. And so we want to put this data in terms that most people can understand. So in terms of square footage of conditioned space, or for example, tons of dry drain. And finally, we want to describe the carbon dioxide emissions reductions potential, since climate change is an important driver in this type of activity.